So in this video, we are going to look at the difference quotient that we used in the previous homework assignment to calculate slopes of secant lines. And we're going to look at how to use the difference quotient to find the slope of a tangent line. And the process of using the difference quotient to come up with the slope of a tangent line, we're going to define the derivative of a function. So probably the best place to start is just to review what we were doing in the previous homework assignment and the previous set of videos. So in the previous homework assignment or video set, we were looking at a function f of x. We still have problems with my pen tab today. So we looked at a function f of x. We put 2 points on the function, x sub 1, y sub 1, x sub 2, y sub 2. And then we identified that the secant line was just a line through those 2 points, or that intersected our function f of x in those 2 points. And these points can just be arbitrary points on the function f of x, which is why we represent them as x sub 1, y sub 1, and x sub 2, y sub 2. And what we did next is we identified that we could find the slope m of that secant line by using the classic change in y over change in x, or delta y over delta x, where we take y sub 2 minus y sub 1 and we divide it by x sub 2 minus x sub 1. And when we calculate the slope of the secant line this way, we're working over the interval that starts at x sub 1 and ends at x sub 2. So this is the closed interval over which we're working. So let me get rid of that. And then what we did next is we said we're going to want in the future to find slopes of tangent lines. And this method for calculating the slope of a line isn't going to lend itself towards, in most cases, finding the slope of a tangent line if we're interested in it. So what we did is we came up with a second way to find the slope of a secant line. We said the slope m of a secant line can be found using the difference quotient, where we do f of x plus h minus f of x over h. And this formulation for finding the slope of a secant line is related or equivalent to this method for finding the slope of a line. And it's related in this way. We work over the interval from, instead of x sub 1 to x sub 2, it's from x to x plus h. So we work from x to x plus h. So the x is x sub 1. The x plus h is the x sub 2. And then h, if you recall, was just the difference or distance between x sub 1 and x sub 2. So h was equal to x sub 2 minus x sub 1. And with these characteristics in place, this calculation of the secant line is equivalent to this calculation of the secant line. It just looks different. So the issue is going to be when we want to find a tangent line. So let's say instead of wanting the secant line through 2 points on the function, we really want to find the slope of a tangent line at a specific point. So suppose we want the slope of the tangent line at the point x sub 1, y sub 1, or in other words, at the point x. Pen tab is really giving me fits today. At the point x, input x, output f of x. That's not very smooth. So let's say we want the slope of this tangent line. And remember, this tangent line is a line that just touches the graph at a given point. So the idea here is that we can actually think about finding the slope of the tangent line by looking at the slope of the secant line. So what we want to do is let x sub 2 get closer and closer to x sub 1. So if you let x sub 2, the x coordinate on this point right here, if you let x sub 2 get closer and closer and closer to x sub 1, you can see that the slope of the secant line becomes the slope of the tangent line. So what we want to do to find the slope of a secant line is we want to find the limit That's just breaking my heart that it's doing that to me today. This is my 4th attempt at shooting this video because of pin tab issues. So we want to find the limit, maybe if I draw larger, as x sub 2 gets closer to x sub 1. We want to take and let the x coordinate, we want to let this x coordinate for this point get closer and closer and closer to x sub 1, so that the slope of the secant line approaches the slope of the tangent line. And if we take the limit as x sub 2 goes to x sub 1, as x sub 2 gets closer and closer to x sub 1, in this formulation, if x sub 2 gets closer and closer to x sub 1, then the h gets closer and closer to 0. So as I let this point get closer and closer to this point, the value for h right here, which is just the distance between x sub 2 and x sub 1, you can see that the h goes to 0 when as the secant line becomes the tangent line. So taking the limit as x sub 2 goes to x sub 1 is equivalent to taking the limit for the difference quotient, taking the limit, man, that's just killing me, taking the limit as h goes to 0 of the difference quotient. So we want to take the limit as h goes to 0 of f of x plus h minus f of x all over h, which is the same as taking the limit as x sub 2 gets closer and closer to x sub 1 of the ratio y2 minus y1 over x sub 2 minus x sub 1. And when we take this limit, the delta y right here divided by the delta x right here, as x sub 2 gets closer and closer to x sub 1, we identify, we kind of rename delta y and delta x as dy over dx. And if we write it like this, this means that we've taken the limit as x sub 2 approaches x sub 1 so that the change in x becomes infinitely small and the change in y becomes infinitely small. So these are equivalent statements as long as we've taken the limit as this change in x, which is the same as h, if we've taken the limit as h goes to 0. So to summarize, to find the slope of a tangent line, we let h go to 0, which causes x sub 2 to get as close as you want it to get to x sub 1. And you can see that the secant line, as h goes to 0, or x sub 2 approaches x sub 1, the slope of the secant line approaches and then becomes, in the limit, the slope of the tangent line. So we summarize what we've just done, hopefully by opening this up and wiping that screen clean. To find the slope of a tangent line, we take the slope of the secant line from the previous homework assignment or set of videos, the slope of the secant line using the difference quotient. And all we do if we want the slope of the tangent line is we take the limit as h goes to 0 of the secant line slope formula from the previous set of homeworks. And then there's going to be, we're going to call this limit right here is going to be the derivative of the function f of x. Derivative is the slope of the tangent line calculation. And there's going to be different ways that this can be presented to you. It can be called the instantaneous rate of change, which we'll talk about later. F prime of x, so writing f with the little apostrophe right there, and then x is another way of saying find the derivative of the function, or take the limit as h goes to 0 of the difference quotient. Dy dx, which is really the delta y over delta x from the slope of a line. When we take the limit as h goes to 0, we rewrite delta y over delta x as dy dx. And then sometimes Instead of f of x, you use y to represent a function. And if we do that, then the derivative f prime is going to be also represented by y prime. So when you're asked to find the derivative, it can be thrown at you a lot of different ways. Find the slope of the tangent line. Find f prime of x. Find dy dx. Find y prime. Find the instantaneous rate of change. Those are all different ways of telling you to find the derivative of a function.